All right, so before we jump into material here today, couple of things. So someone sent me an email yesterday and asked me a question. So my mistake will be your gain. I accidentally in the announcement said that the assignment was due by 11:30 p.m. I meant for it to be due by class time, which is 11:30 a.m. So I'll extend the due date on that to the end of the day today. So I'll get that updated when I get back to my office here. But you can submit that by the end of the day today. So a little bit of an extension if you didn't quite get that done. I'm also gonna try not to be frustrated. So I've been trying to constantly ask if everyone's making sure that their state is working okay. Come talk to me if it's not. I'll try to walk through a little bit more, some confusion that I'm seeing. But you know, when I'm getting an email that you can't open the data file the night before the assignment's due, that doesn't give me a lot of time to help you, right? So when I'm seeing emails coming in at 11 o'clock at night, I probably shouldn't be awake, but it doesn't give me a lot of time to kind of help you. Stop in my office hours, which a lot of you have, we've been able to resolve like the issues, get everything up and running. So start these assignments early, right? You don't wait until the last day because it's a new program, you haven't used it before, and you're gonna run into issues, and then I don't have time to help you. So if I didn't make a mistake and the due date was before class today, you know, if you email me the night before, don't give me I teach all morning, I don't have any time to kind of get a good response to you, okay? So with that in mind, I'll mention a couple of things that I'm seeing. So first of all, what you're going to upload for the assignment is a what? A do file. You're not uploading the data set. I have the data set. I gave it to you, right? You're not having to make changes, saves to that data set. You're just starting with it and then getting a bunch of different statistics from it. Now, how you get those statistics, that's going to be from your do file, which we kind of said this little notepad, right? So whatever, when you start this assignment, there's no do file to open. You're creating it, right? That's going to be what you eventually upload. Now, if you try to open data files from the do file editor, so go to my OneDrive here. Sorry. So if I look at all files, okay, I've got to open up this traffic. For you, it would be the GPA data. If you try to open this up in a do file editor, this is what it's going to give you. I don't even know what all this means, right? Basically, this means that you're trying to open up a data file, treating it as like it's a do file. The only way you open up data files is through the actual Stata program where you go to File, Open, and now you can open up different data files, right? Now that you've got that data file, we said we can kind of look at that browser. It's sitting around behind the scenes here. Now I go to that do file editor and I start to type my code that's then I'm going to execute. So I don't even know what the variables are. What's one here? Let's do one. Actually. Right. Then I've got my code in my do file. I execute it. It then runs it in the program. And now I've got all this code that I'm turning in that shows me you know how to get Stata to tell you the different statistics you need. But I also need for you to grab the statistics from the output and tell me, because if I ask you for the mean, and I don't know, you look at this and you know, this would make more sense when we progress later on in the semester. It's very easy to find the statistic you need now, but right, I need you to report to me that value. So some people are doing that using the comments in the do file. And if I'm saying this and it feels like you've heard this before, I apologize, but there are people asking questions. So I would say, you know, mean is 0.91, right? You can do this part in a separate Word document if you want to, and then upload both of those. But you need to have both your Stata code saved in this do file and uploaded, and then the answers at least somewhere in this do file as comments or as a separate Word document. Okay. Now, also, I feel like I've said this a million times, so hopefully I'm not like making this up. But the only place you can open up data files from is where? They have to be on your OneDrive, right? And I feel like I've said this a lot. I'm getting emails, I can't open it up from my personal device. You can't. Never told you could, right? That's the whole reason why you had to go authorize the cloud storage, why you had to create a folder and drag the files or copy the files over to your OneDrive, because you can only open up the files from your own OneDrive, okay? So, you know, I don't know if I can say it more plainly. You can't open up any file that's not on your OneDrive. So when you download the files from Canvas, they typically will default to go to your download folder. So what do you need to do? you need to go to OneDrive and then kind of upload them from your download folder, throw them into your OneDrive. Okay? Yeah.
If I can open it from my local disk and the data is all correct, is that fine?
Yeah,
I don't know why.
I said, I don't know how you're able to do that, but yeah. You might have it. Let me think why you could do that. Are you sure it's not under, it might look like it's on your, under like this PC, but if you've synced up your OneDrive, it'll look like it's part of your, like a drive on your computer, but it's actually, yeah. But if, yeah, that's fine. But for most, you got lucky. Because I think for 99% of people, you're not going to be open. I can't open up anything on this computer if it's not in the OneDrive, right? Okay. So got the rest of the day to kind of work on that. You know, not super available. I'll try to maybe look at my inbox in between classes before I teach later this afternoon and kind of get some answers sent out. Moving forward, start these problem sets early. Also, one other issue that I have seen arise for people, and I apologize for not anticipating this, is when you're saving to your OneDrive, if you save your do file and you use any type of a symbol, it looks like it's saving it, but it's not saving it as a do file. I don't know why it doesn't like symbols. So like anything you have to hold shift and use one of the number keys for, so an @ sign, and sign, any of those symbols, you can't include those in your file name. Otherwise, like I said, it looks like it's saving, but it often then just goes away, right? Or it's not saved as a do file. It's like a .do something else. It freaks out. I have no idea why it doesn't like symbols, but it doesn't. So instead of doing that, you can save it as problem set 1. So just avoid using kind of, you know, and like I get the confusion because I think the Word document I gave you had problem set number 1 in it. But when you're saving your do files, avoid using any symbols. Okay. And in fact, that might be really nice. And I'll extend the due date to the end of the day tomorrow. And I have office hours tomorrow. So if you do have any last minute questions, you can kind of stop by. I guess it's give you a little more time to do that because I want to make sure we're all kind of getting comfortable with SATA because we're going to use it kind of here on out. Okay. So I'll change that even not to the end of the day today. I'll change it at the end of the day tomorrow. That gives you a little bit of time to kind of get some more help from me. Also, me to just kind of respond to some more of those emails if I see them come in. Okay. All right. Any other questions from me before we kind of jump into material here today? Okay. So, how do I want to do this? We're just going to start right off with a doc hammer. So we talked last week about running regressions. In fact, before we dive into this discussion, just get kind of a refresher. So the file that we're going to be using this week should be up there on Canvas and is called I'm taking my sweet time, hold on. MLR in class. Okay, so that's the do file I'm going to have opened up. I could go and file open and out a little bit, so this isn't so crazy. So we're going to go down here. Oh, actually, no, we're not going to do this yet. We'll use the file from last class. So we're actually going to use start out today. Sorry, that's the next one we'll go into for the rest of the week. The one we left off working on last class was regression in class. So I've kind of got these file paths set. You could just go to file open. But I'm going to set the path because I know it's always the same. We're going to use that COVID County data that we opened up last week. So I'm going to run those codes. Notice it's putting the code in there, running it. It's now got all that COVID County data. Oops. So we said that we can do things like run these regressions. And so for here, I'm going to go down what we'll talk about today. So we could run these regressions where I was looking at like the cases per person. And then I had this other variable, which was metro, just 1 if it was in a metro county, 0 if not. So this is my Y variable or my left-hand side variable. This was my X variable or my independent variable. We could run this regression. We then get these slope coefficient estimates. Right? So we're trying to estimate this line of best fit. The value for the intercept and the slope that would kind of give us this line of best fit that minimizes some of the squared errors were these two values. Okay? That's kind of where we left off. Now, when we have these coefficients, we said, what do we always assume that slope coefficient true value is? So we always start out assuming that the relationship between x and y is not positive, but nothing, zero, right? We're stacking the deck against ourselves. We're assuming that there is no relationship. So if we can reject that, what we're saying is we found evidence that there is a strong relationship. How do we know if we can reject? Well, Stater reports to us, first of all, it takes that coefficient, the sample statistic, subtracts the assumed true value of the statistic, is always zero, and then divides by our standard error. Just like we divided by the standard deviation of our sample mean to get our test statistic, here we're dividing by essentially the standard deviation of our slope coefficient, referenced as the standard error. That's kind of the terminology we use for it. That would give me my test statistic. I could then go look that up in the t-table, find the area more extreme than it, multiply by 2 to get my p-value. So we're always doing a two-tailed test where we assume that the value is equal to 0. Okay. So just so you guys relate, it's really important to me on time. I'm not going to run back through it. I said some pretty important stuff at the beginning of class. So just from here on out, try to get here when class starts. I generally go through some kind of housekeeping stuff. That's stuff that you guys probably want to know. So you might want to ask me a question after class. So you've got a test statistic, right? You get that p-value. How do you make your rejection decision? If that p-value is less than the alpha you set. What 3 alphas do we generally use? 0.1, 0.05, 0.01, corresponding to 10, 5, 1% significance levels. So that's where we left off. The problem is, sometimes when we run these regressions, we can have a variable. I also have markers that are dying. Yeah, that goes. We can have a variable. So we'll call this x, we'll call this y. And maybe it looks something like this. I'm just plotting like a scatter plot of all the different observations that I see for x and y. I'll try to really make this pronounced. Okay. So here I did one where if everything works correctly, it should be that the distribution that we see for these estimates of that slope coefficient should be centered around that true population slope value. We can't see this because we don't have population data, but that's what our sample slope coefficient should be centered around. So we also are going to have some standard error associated with this, or I said you can think of it as like the standard deviation of the slope coefficient. It's not completely what it is, but it's easy enough to think about it that way. It's the same kind of idea, right? What's the variation we would see in those slope coefficient estimates? The problem is, if we have a line of best fit, and here got kind of a weird one, but like kind of horizontal, right? We said last class that we want the expected value of our errors given these different x values to be 0. So we're making equally as bad. Remember, what was this line of best fit? It was essentially our predicted y values. Okay? We were running this regression, minimizing the sum of the squared errors, getting our slope and coefficient estimate values so that we could come up with these predicted y values. We said our errors were the difference between the predicted y values and our actual y values. So notice here, for like this value of x, I'm making a lot of errors here. Here's my prediction. Some of my errors are negative, some of them are positive. But there's like equal amounts on either side. So this was the idea that the expected value of our errors, no matter what x value we're looking at, looks like they're about 0. Okay? Now what can happen, right, is that if I'm looking here, yes, the expected value of my errors are 0 because these errors are kind of offsetting. These ones I'm making predictions that are too low. These ones I'm making predictions that are too high. So when I kind of add them up, find the mean is going to be 0, right? They're offset. But what do I notice is true about errors that I'm making for this lower value of x? It's a pretty wide range, right? I'm making some really large errors one direction, some really large errors in the other. What's true about my errors once I get out to these higher x values? I am making errors on either side, but they're really small. So the variation in my error term depends on what values of x I'm looking at. right? Oh. Okay, so the variation of my error term depends on the different values that I'm seeing for X. For really low values, there's a wide range of errors that I could be making. For these higher values, my predictions I don't have as wide of a range of errors. So this is going to be the variance of my error terms given these different X values. It's not equal to some constant value. It's not the same for when I write kind of this conditional. So this is given that X has occurred. So given different values of X, the variation in our errors is not always the same value or not a constant value C. Right? If it was equal to C, this is what we would call homoscedastic errors. And everything with our estimates, our test statistics, everything will be just fine. Okay? So if it's instead what we call heteroscedastic, and I've got some slides associated with this too, I just kind of want to start out here, then we're going to have some issues. So we'll talk about what those issues are here in just a second. Okay, so let's go to the slides now. So if we had homoscedastic errors, that variation in our error from our prediction, our line of best fit, is going to be the same no matter what X value we look at, right? That's great, right? Now, what would that look like visually? I kind of had like a easier one. So here, notice like if I were to just draw out the distribution of the errors I was making for every observation, these are all kind of like the same distance, right? They have the same variation, right? These look, they're drawn identically. For different values of X, the errors have the exact same distribution, right? Or the variance is exactly the same. Heteroscedastic errors would say, okay, look, when values of X are low, here, the variation I'm seeing in my errors, that width of the distribution, is a much tighter distribution than when X is high. When X is high here, I'm getting a much wider distribution. Wider distribution means the variance is going. So if I've got a wider distribution, that means extreme values are more likely. So I'm seeing a larger variance. So here, my variance does depend on the values for X. So that's not going to matter for the value of our slope coefficient. But what it will matter for, and we can kind of come back to these in a second here. What it will matter for is when I'm calculating my test statistic, that heteroscedasticity in my error term messes up my standard error calculation. And so then that's going to inflate my test statistic. If I have a larger test statistic, what's happening to my p-value? So a larger test statistic, what's the area then to the that's more extreme than it? Smaller, right? If I'm getting more standard deviations away, that means the probability I'm seeing that or anything more extreme, smaller. So what is this going to make it more or less likely I can reject the null? So if I have a smaller p-value and I only reject when the p-value is less than alpha, I'm going to be more likely, right? So when we have these heteroscedastic errors, we can kind of see it work in the opposite direction. So we're going to be concerned with this. I'll kind of show this to you with data. Oh, I put errors are larger. This should say standard errors. So when the standard error is larger, you end up with a lower test statistic. I apologize. Let's be complete here. Standard errors. So when the standard error is smaller, remember to get our test statistic, we divided by it. So when they're heteroscedastic, it's going to be a smaller value, which then inflates the test statistic, makes the p-value smaller, makes it kind of more likely or easier to reject the null if we don't have these homoscedastic errors. So how do we solve for this? All right, we've got stata, we've got a pretty easy solution. So I'll kind of show you those graphs here in a second. Sometimes I put things in the slide that I know I'm going to do in class that you can just kind of go back to and have them saved. So we go to that regression in class file. The first scatter plot I kind of had in there in the slides. I was just looking at cases per person and vaccinated, and I threw in like a conditional here just because it made it a little bit easier to look at, because there were a lot of values where the percent vaccinated was above 60 in this data set. So now if I'm looking here, I don't know, these are pretty homoscedastic. I mean, if I'm looking at different values of X, the range of my errors I'd be making if I had like this line of best fit, looked like it's about the same variance across all values of X. But I don't want to just eyeball this, right? you know, if I looked at a different relationship, so this is just creating a scatter plot between these two variables. Well, this one, eyeballing it, probably a lot more likely to say that the errors are heteroscedastic here, right? Much wider kind of range of the actual y values or low values of the x, much tighter distribution for higher values. So I'm concerned then if I run this regression, my standard errors aren't going to be right, my test statistic won't be right, my p-value is not going to be right. So what can I do? Well, the first thing, before we solve for it, we can actually identify whether or not we should be really concerned. Because nothing is truly ever going to be perfectly homoscedastic. Like to get completely the exact same, but things will be pretty close. So the test that we have for whether or not we've got homoscedasticity, it's a very hard word even for me to say, is I'll run this regression. So I'm going to try to predict my y variable, cases per person, with this x variable at the percent of the county that's vaccinated. We kind of already looked at that before. We said it looked pretty homoscedastic, but we won't actually come up with a statistic that measures that. So if I run this regression, so I ran this regression, I get this estimate of negative 0.25. Here's my test statistic, negative 11.73. Immediately after running my regression, I can use this SStat-IM test. So what this does is it actually runs a couple different tests, but the one that it runs that we care about is whether or not these are homoscedastic errors. So what we actually start out assuming the null hypothesis is that we have homoscedastic errors. Before we try to correct for them, we always assume that they're homoscedastic. If we can reject that, we're saying we found evidence that there's actually heteroscedasticity in the errors, and that's something we're concerned with. So when I run this SStat-IM test right after I run the regression that I'm interested in, looking for heteroscedasticity in, I get some skew and kurtosis measures, but I also get this heteroscedasticity p-value. So, it goes back to the exact same thing. How can I reject the null? The p-value is less than alpha. So I'm starting out assuming that I have homoscedastic errors. At what level can I actually reject that at? So my p-value is 0.07. So our three benchmarks, which of them can I reject at? Yeah, so when alpha is 0.1, or at the 10% significance level, I can actually reject the errors are homoscedastic and say, I found evidence that there's actually heteroscedasticity. And that's something we want to correct for. Now, I can't say that at the 5 and 1% significance level. So there's evidence that there might be, but it's not real strong evidence, right? So what do I do? So I'll skip this here for a sec. Well, actually, I want to get the output back up there. So we're going to run the exact same regression, just so we can see this output again, right? And then what I'm going to do is I can run one of two different commands. They both do the exact same thing. I can do comma VCE robust or just comma robust after I run my regression. I'm just going to run one of them so we have less on the screen here, but I'll show you if the other one works in a second. Now, when I run this regression, it essentially identifies the heteroscedasticity that existed behind the scenes and corrects your standard errors for it. So notice what's happening here. Once we correct for that heteroscedasticity, our standard errors are actually going to be a little bit higher, right? So we've corrected for it. Before when we weren't correcting for it, our standard errors were a little bit lower, too low. We said that did what? If I didn't correct for it, it gave me too high of a test statistic. What happened to my test statistic once I corrected? Sure enough, it's smaller, right? Smaller in absolute value, right? We're talking about absolute values here, just closer to 0. Now, the p-value looks like it didn't change, but that's just because it's really small, right? And in fact, this is kind of a good point. If I asked you what happened to the p-value here and you told me it didn't change, it's not right. Because if I look at that test statistic, I can see there's a difference in the test statistic. So if my test statistic is a little bit smaller, my p-value has to be higher. So once I correct for this, it's actually, I have a slightly higher p-value. It's a little bit less likely I could be rejecting the null. It's an easy fix, right? Just comma robust. We don't have to worry about any of the math that goes on behind the scenes. Right? So that the kind of key takeaway here, because I will get up a problem set after class today. It'll be the second problem set. If you want to test for heteroscedasticity, it's just running this SStat-IM test after you run your regression. If you then find evidence that you have some heteroscedasticity, right? You can reject the null that the errors are homoscedastic. all we have to do is throw in this robust command, right? And it'll correct everything for us. Now notice, I actually end up with the exact same slope coefficient estimate. It's just the standard errors, and then that affect the standard error, that affects, has cascading effects, affects the test statistic, the p-value. But the slope coefficient estimate isn't impacted by this heteroscedasticity. It's just our statistical significance that's impacted by it. But it's an easy fix, right? Any questions over anything there before we keep moving? Okay. All right. So, is there anything else you wanted to say here? Don't think so. Oh, I did want to make a point. So let's say I got this p-value and it's like 0.11. What levels could I reject at? So if my p-value is 0.11, which of my conventional levels can I reject at? None of them. So I can't really reject that the errors are homoscedastic. In practice, let's say that p-value of 0.11. Oh, okay, I can't reject it, so I don't have to correct for it. Well, what levels could have you rejected at? I mean, you were really close. So remember, the 10, 5, and 1 are like saying things with 90, 95, 99% confidence. The p-value was 0.11. I actually could have rejected it at 9 or 88%. 88% is still pretty high, right? So we're going to start to talk about things even with like the coefficient estimates, just because they're not quite statistically significant. If they're really close, that doesn't mean we should just completely ignore them, right? In practice, what we maybe want to do, go out and get a higher sample size, right? We know that's going to kind of allow us to like pinpoint down exactly where that value is a little bit more. So we don't just want to completely ignore it just because it doesn't hit our thresholds. If it's really close, probably err on the side of caution. If I found a p-value of 0.11, in practice, guess what I'm probably doing to my standard errors when I run my regression? I'm going to use that robust command to correct for the heteroscedasticity because it's, pretty close that I could actually say the errors aren't homoscedastic. Like I'm really close to being able to reject.
You go back and say, why robust command is to file.
Yep. So you can do it one of two ways, just comma robust, right? Or you can use this VCE package. So I'll show you that this one runs too. And it gives you the exact same value as we had before. That VCE just behind it, we'll use it for some things later on the semester. It's basically like a bunch of stored. The VCE would give you options to do a lot of other things other than robust. The comma robust is just, that's all it can do. Yeah.
Just to confirm, when we use the robust command, it increases our test statistic or it increases the active value.
So when we use the robust command, the whole reason we were using it is because we knew if we didn't, where's that? There you go. Our test statistic was actually too high. Our standard errors were artificially low. So once we correct for it, it will actually increase our standard error and lower our test statistic. Yes. So, when we correct for it, it's also like we always, we're starting out assuming that there is no relationship between X and Y. It's like we stack the deck against ourselves and assume that there's no relationship. Same kind of thing here. We want to make sure that we're controlling for everything that makes it, we want to make it like less likely we can reject the null. So that then when we actually do reject it, it has more meaning. So by correcting for those heteroscedasticity, well, now my standard errors, we call robust standard errors. Now it's going to be a little bit less likely I can reject the null. Any questions on this before we keep moving? Just out of, because I showed this other one to you. So what was the other one we had? So this is where instead of typing things out, and this gets me into trouble sometimes, but copying and pasting is often helpful. So actually, second regression here. So I just wanted to kind of show you another example. So let's say I wanted to regress or use the shorthand REG, median household income on the unemployment rate. This was the one that we said looked a little bit more kind of homoscedastic. So I can actually test though whether or not it was. So I think the one that I showed you, I also truncated some stuff. So this is using all the data. So I'm going to run that regression and then run that test to get my p-value for my test for homoscedasticity. We'll notice, sure enough, my eyeballs were working kind of right, actually working very wrong. So my p-value is 0 here, right? So I very clearly can reject the null. I'm rejecting that the errors are homoscedastic. I really need to make sure I correct my standard errors here. So if I go back here, copy my, oops, it's not allowing me to use my shorthand. There we go. And then just kind of throw in this robust command. What should be happening to my standard errors? They should be a little bit larger. My test statistic will then be a little bit smaller, and my p-value would be a little bit larger, right? So we'll see if those things hold. So notice I get the exact same coefficient estimate, but my standard errors are now a little bit higher. I say a little bit, quite a bit higher in this example, right? And that's because, remember, I was rejecting with 99% confidence here. That p-value was less than 0.01. I could reject it that, highest, I could reject that significance level of 1%. So I really should be correcting. So sure enough, my test statistic goes from -28 all the way down to -22. Now that's still a relatively large test statistic, so the p-value looks the same. But we know that for a smaller test statistic, that means my p-value is actually gone up. Yep. Okay. Any other questions on this before we're kind of switching gears a little bit? Yeah.
Yeah, sorry, can you just re-explain the p-value on the E-stat item test? Can you just kind of re-explain what that means?
Yeah, so you can think about it this way. When we run that test, our null hypothesis, and I'll write it out technically, is going to be that the variation or errors given different values of x is always the same. Or what we're assuming with our null hypothesis is homoscedastic errors. So when we are doing a hypothesis test, we only reject when. I feel like probably getting tired of me saying this, but when the p-value, I'm trying to beat this into your head, when the p-value is less than alpha, right? So that p-value is telling me if it's 0, well, that's going to be less than any of my conventional alpha values that we use, right? So if I can reject the null, I'm saying I'm rejecting that the errors are homoscedastic. I found strong evidence instead that they are heteroscedastic. Does that help? So it's just, any statistic that we have, what we're getting from sample data, we're going to have a p-value associated with it, right? And then we can kind of do some type of hypothesis test. Yep. Any other questions before we keep moving here? Was the doc cam on at all during that? There we go. Sorry, that's probably a little more helpful. I didn't realize it wasn't going. I got too intense into what I was talking about. So here, my null hypothesis was that the errors were homoscedastic. So I'm basically just using that p-value that Stata reports to me, right? It was running a test for whether or not that variation in error terms was just a constant value. If I found a p-value low enough to where I can reject that null, I can say, okay, I found evidence that the null isn't true. I'm rejecting it. So I'm rejecting the errors are homoscedastic. I found evidence they're heteroscedastic. I need to use that robust command. I need to correct for that in my standard errors. Does that probably help to make a little more sense now that you can see that? Yeah. Okay. All right. Any other questions? Yeah.
So you're saying that when you find that the results are heteroscedastic, then you do the robust command.
Exactly. And I find they're heteroscedastic when I reject that null. So once I reject the null, that's evidence that I need to then use that robust command to correct for the errors that were, for the incorrect values in my incorrect value of my standard error. I don't want to use the word errors too much and get it confused. Yeah.
So you use the robust command, right? It's
Correct. So if I reject the null. Yep. Okay. Any other questions before we switch gears here? So everything up to this point is going to be something that I could expect you to do on the next quiz, which I think I mentioned last class. I put up the next sample questions. So we've already talked about a lot of it last week, so you can start working through those. I'm going to put the next quiz up after class today. That'll be due before we meet in class next Tuesday. So I have a week to do that quiz, right? The actual problem set, I'm gonna have you set to do the end of the day next Friday. So you have like a little bit more than a week and a half to kind of work on that. It'll all be based off of simple linear regression. And then like the final questions would be what we just covered right now, heteroscedasticity, okay? Okay, so let's push on. So I'm not gonna waste too much time with this in the sense of like, I'm not gonna specifically ask you like questions over this, but we've got a bunch of assumptions that we need for the statistical significance of our estimates to be valid or to be making the correct rejection decisions. So we kind of would say, one of these assumptions is that the errors are homoscedastic, right? If they aren't, then we knew our standard errors were going to be wrong and we had to correct for it. So I think if you look it up, this Gauss-Markov theorem says we need them to be homoscedastic in order for our estimate, slope coefficient estimate to be what they call blue, a biased linear, or sorry, best linear unbiased estimator. I forget the acronym even stands for. Now what ends up being kind of helpful is, it's hard to get, we see heteroscedasticity in our errors a lot. So a lot of the times we're not going to have a blue estimator, right? It's not going to meet that. However, if we get really large sample sizes, even with heteroscedasticity, everything kind of converges to the results we get from homoscedasticity. So that difference in your test statistics, the difference in those p-values, it essentially is getting closer and closer to zero, the larger the sample size you have. So once again, we work with pretty large data sets, there's a lot of data out there. We maybe aren't as concerned with this as the people over in biology when they are running their experiments with, or I shouldn't say biology, like psychology, like, maybe you only have 20 participants or 40 participants, like you got to be a lot more concerned. When we're dealing with really large data sets, we don't have to be as concerned. Right? So I'll go through this quick so I save time for what I think is a little more difficult because we kind of already talked about this in week 1. So we had this idea of correlation versus causation, right? So we needed a couple things to be true in order to truly have a causal relationship, right? So we need the expected value of our error term given different values of x to be 0. I kind of mentioned at the beginning of class, right? Our line of best fit, we should gonna have equally as many errors that we're making too low with our prediction as we have errors that are making errors that are too low, equally as many errors that we're making too high with our predictions. We also need to have kind of these two variables be identically and independently distributed. So their distribution, if we're randomly sampling, is not going to be dependent on each other. We also can't have really large outliers, right? Especially with smaller data sets, really large outliers can greatly influence the results, right? So like if you're doing anything with like wages and all of a sudden you randomly sample, or I shouldn't say wages, household income, and you randomly sample Elon Musk, it's going to screw up your results, right? I actually saw, I think the other day, he's like on the verge of being a trillionaire. I think that I saw a report, so good for him. Also, we can't have all of the X values be the same. I'm never going to try to trick you and give you a data set like this, but we can't run regressions if X is 10 for every single observation. We can't do it, okay? Because there's no variation essentially in our data, right? Absolutely zero variation. So we'll end up, I think, I'll use the term later on in the semester, but you might see this reference as basically called multicollinearity. So anyways, actually this would be just collinearity. We'll talk about multicollinearity later on. So we're wanting to move from linear regression, which is evidence of a correlation, to we want to try to get more causal interpretations and effects. So we're going to go to that multiple linear regression. So all we're doing is adding in more variables on that right-hand side. So for example, if you think about a very naive regression where I'm leaving off this population variable, right? If I were to just run a regression of the number of police officers in the county and the crime rates in that county, I find a strong positive effect. Right? In fact, I think I have my slides in just a dumb order here. So skip ahead a little bit because I have the results so we can actually talk about them. So if I run this very naive regression, it's going to look like having one additional police officer. So we're doing a lot of interpretations today, just getting more examples so we get used to this. So 1 unit change in X, having one more police officer in your county, actually looks like it increases the predicted crimes in that county by 33. Well, that doesn't make it like having more police officers around, actually crime goes up. Well, I'm not controlling for anything else. A city like, what's a local one? I live up kind of towards Ellettsville, and it's not even super small, but thinking, you drive through rural Indiana, you'll go through a town. And you're like, there might be 500 people that it feels like that might live in this old town, right? They probably have one police officer. They have a low number, they probably also have very low crime. If you go to counties around Indianapolis, they're gonna have a ton of police officers because they have a lot more crime. So we should, we're not controlling for anything else. So what if we controlled for one more thing, which is just, well, what's the population of the county? We know that if I have 500,000 people, or 500,000, 500,000 people in my county, I might need more police officers, right? So once I control for that, notice what's happened to my estimate, it's dramatically lower. Now, it still looks like having additional police officers is going to increase crime, but once again, we've only controlled now for one other thing, which was population. Okay, so this just kind of highlights how our slope coefficient estimates will start to change as we add in more explanatory right-hand side X independent variables, all terms for kind of that right-hand side of our regression. And it kind of makes, if you think about it, we're not just using more things to make our predictions. So I wanted to show those results since I had mentioned this example here. So I'm starting to include these additional variables. So I include population, right? I include maybe, median income in that county. I can include as many variables as I want here, n. Technically, that's not correct. I can't have more variables than observations, but we don't often run into that problem. So how do I find my intercept, my intercept coefficient, my slope coefficient for both of these variables now? Well, it's the same exact problem we had with linear regression. We're going to minimize the sum of our squared error terms, right? What was our error? Well, it was just the difference between the actual and the predicted y values. Okay? I'm then going to, how was I coming up with these predicted y values? That was just my kind of regression. Right, that's how I was making my predicted y. So just as kind of a reminder, what we were doing last week, we were finding these intercept and slope coefficient estimates using stata that gave us this line of best fit, and that line of best fit was making predicted values of y for different values of x. Right? All we're doing now is we're making our predictions also using an additional variable. So just as a kind of more of a thought experiment, if I'm including more explanatory variables, I'm adding more things into my predictions, what do you think is probably happening to the errors that I'm making? Just take a step away from statistics for a second. If you have more information, do you think you could make better or worse predictions? Better predictions, right? So if I'm adding in more data, more variables that might help explain why, my errors that I'm making with my predictions are probably going to be a lot smaller. So we want to include more of these variables, and hopefully our predictions are then going to become more and more accurate, right? Which is ultimately like what we want. I had someone stop in yesterday and we we're kind of talking, but you can use data to, if you can get a bunch of additional variables on the right-hand side, you can start to predict things like economic downturns. I've got a small project I'm kind of working on. I haven't had a lot of free time to do it, but you can take like betting lines and you can look at like previous outcomes and then predict which betting lines are more or less likely to, you can make money off of it, right? So we want to, if we have all these additional variables, we can make better predictions, right? That's our end goal. So here, we're going to minimize the sum of those squared error terms, right? Just plugging in how we're making our predictions. We're using this regression equation, not just with two variables, but however many we want to include there. Now, what we did before was we only had the intercept and the slope. We took a derivative of that function in respect to those things, two equations, two unknowns. We can maybe even do that math ourselves a little bit. The math, when you have n plus 1, right? N variables plus your intercept, n plus 1 equations, n plus 1 unknowns, this is not fun to calculate, right? But Stata can do it behind the scenes for us very, very quickly. Okay? So our prediction now looks something like this. Right? So let's say I've got my predicted y value, and all of a sudden we're now thinking about how do I interpret now a change in that x1 variable. So before we would have said a 1 unit change in x changes our predicted y value to go up by beta 1. So think about if we had a change in x, what would our prediction be? Well, it would be whatever it was before, plus whatever that change in X was, right? Our X value would be whatever the old X value was, plus the change in it. Right? So what's the difference in between my prediction before the change and the prediction after? Well, notice if I take the difference between these, this cancels, this cancels, this cancels, the error term would cancel. The only thing that I have, and I shouldn't have the error term written in there, but I copy and paste it, forgot to delete it. So I'll do this and save it. So this was the actual Y value. I was copy and pasting functions so that I didn't have to type them all back out. So the only difference between these two is going to be beta 1 times that change in X, right? So our predictions, we still are going to interpret that slope coefficient beta 1 the exact same way. It's the impact or the change in the predicted Y value from a 1 unit change in our X variable. And don't worry too much about this. It's kind of just a different way of thinking about these changes in X and how they're going to change my predicted Y values. The only thing that's operating right, you can kind of think about it here. This is the same no matter what. When X1, that variable X1 is changing, my predicted Y value is kind of getting changed the same amount by X2. That's a constant, right? It's staying the same. So now we have our interpretation of our slopes. It's the exact same what we were doing before, but now we get to add on this additional phrase. I don't have it in here, but now we add in this additional phrase, holding everything else constant, right? So this becomes a lot more powerful of a statement. So if I'm thinking about going back here, now my interpretation of beta 1 is here's the effect of having 1 additional police officer, a 1 unit change in X, on the predicted crime rate, holding constant the population. So the thought experiment now is, well, this is the impact that having 1 more police officer would be if I took 2 counties with the exact same population, but one of them had 1 additional police officer. What would the change in their predicted crime rate be? That's a much more powerful statement. And that's only including one thing. I could then say, include multiple variables. So we'll go to an example here. Where, and I also didn't add in what the Y variable is here, but I'm going to kind of make a point from state to output. What do I know has to be my Y variable? So when I run these regressions, the very first thing I'm always putting is the dependent or the Y variable. So what would my dependent or Y variable be here? Wage, all right? So wage, if it kind of helps, right? I just kind of want to make the point we can get what the actual regression was from Stata as well. It's telling us, here's your Y variable, and then you're including every other variable you list after that. That's going to be additional independent or X variables or right-hand side variables. So now the interpretations of these coefficients, how would I interpret IQ here? So just measured in points. Wage is measured in dollars. I think here it actually was, well, let's just do dollars to make it easier for the interpretation. How would I interpret that slope coefficient on IQ? Yeah.
If you hold everything else constant and you increase the IQ score by 1, your wage will increase by 1.
Yep. And generally, I say it the other way, but you can say it both ways. Holding everything else constant, so holding the age and the experience of the individual constant, having 1 additional point of IQ would predict your wage would go up by $8.41 if we round it, right? So it's the same way we interpreted it before, but now we add in this holding the other things constant. It's not holding everything else constant, it's just holding everything else in the regression constant. Okay. So how would I interpret the experience variable? This one gets to be a little weird. Yeah.
So just a question. So if we saying holding everything else constant, if there was a 4th variable that was gender, but since it's not written there, when you say holding everything else constant, does that include something like that?
It only includes the variables that you've included in your regression. Those are the only things we're holding constant. Remember before when we didn't include those? They were all changed. So anything we don't include, we're not holding that constant. So anything we think might matter is generally a good idea to include into your regression. Yep. I see another hand. No. Okay. How would I interpret my experience variable here? If experience is measured in the years on the job. Yeah.
The amount, the amount each additional year adds to your wage, holding IQ and age constant.
Would be
would be. It would reduce it by 1.4%.
Yeah, so this one's kind of weird. So it's a 1 unit change in X, so having 1 more year of experience actually predicts that wages go down by $1.40. So that's holding constant the age and the IQ of the individual. So it gets kind of weird to sometimes think about these things because I actually believe what happened with this data set, the reason why this result is kind of weird is this was actually an hourly wage data set. So I made it dollars just to make the interpretations easier starting out. But I think it was hourly wage. What do you think most people throughout their life progress out of hourly wage jobs? Who remains? So people with 40 years of experience working at McDonald's are probably the people that couldn't get to the next level, right? And so just because they have more experience doesn't mean they're any better workers. Also, years of experience, right? When you think about what's something that happens, and you guys aren't as, not all of you are kind of like business kind of like people, but like what's a term that people use with their job? You've been doing it so long, you get, well, hopefully you get tenured, but something that makes you not very burnout. Right? So sometimes we'll say, if you do something long enough, you get burnout, you stop caring. If I stop caring, I'm not as productive of a worker, companies aren't going to want to pay me as much, right? So there's explanations. Sometimes these interpretations will seem weird. It also could be the case that, guess what? I left out a lot of other important variables here. I've only got age and IQ. So I'm not holding anything else other than age and IQ constant. So, but that's still how we would interpret that slope. Now, what's also true is what can I actually say with any reasonable level of confidence or statistical significance? Can I say that experience here is actually having an impact on wages? If I look at that p-value associated with the slope coefficient for experience, what is it? 0.66. Is that anywhere close to being less than any of our threshold alphas? In fact, even if I wanted to say something with 50% confidence, that's not less than an alpha of 0.5. This is basically, we didn't find an effect, right? We still have a value to what the actual estimate was, but at any reasonable statistical level, we can't say that experience here actually has any impact on wages. And once again, this was an hourly wage data set. I'm not making these statements about every job. Okay, this is just kind of a unique toy data set here. Okay. Any other questions about anything up here? Yeah.
So I noticed the 95% confidence interval
Mhm.
for the experience, it includes 0.
Mhm.
Doesn't that mean that you reject it? Like
So anytime, so the values in my confidence interval are the possible values for that true population slope value, right? So if 0 is in that range, 0 could be one of the true values. So if I run a hypothesis test, if it could be one of the true values, I won't reject it. Anytime 0 is in our confidence interval, those are going to be situations where we fail to reject. Anytime 0 is not in our confidence interval, well, then what we can say is with 95% confidence here, 0 can't be, and that was what our null hypothesis was that it was equal to 0. With 95% confidence, I'm telling you, the true value is somewhere in this range. So I won't make you guys do this, but you can actually use the confidence, well, later on this semester, I might, not right now. But if I look at this confidence interval, I can actually do hypothesis tests for slope, assume true slope values other than 0. I could actually do one for 5 here. And I could tell you that if I did that hypothesis test, Stata is always going to give me the results for the hypothesis test of if it's equal to 0. But if I did have, is it equal to 5, here I could actually tell you, no, I can reject that value as well. I found that it has to be somewhere in between 6.7 and 10. Does that?
Yeah, I just reversed it in my head.
It's all good. It's all good. Again, it's tricky. Any other questions before we keep moving here? Where are we at in time? Okay, we're pretty good. All right. So, no, I don't want to do that. There we go. I'll run through this kind of quick. We kind of already looked at these. You know, I would think that the sign's going to be negative small. We already looked at this. We ran the regression. It's huge and positive. Why? Now we left out a lot of other important omitted variables. We include just population. It cut it in half. Right. Just another example to kind of start thinking about this because I had a data set that was kind of interesting. I ran, so I have like, I think it's 2012, all the Indiana births that happened. So it's got birth weight in grams, and I had this mother's smoke variable. which is a 1 if they smoked during the pregnancy, 0 if not. And this was like detected through blood and screening, so this was, I mean, not like a self-reported thing. This was actual that they were found to have been smoking or at least ingesting tobacco of some kind at some point in the pregnancy, which in general we can think about as probably a bad thing for the baby, right? So birth weight is generally a good measure of health of the baby. So higher birth weights are good, lower birth weights are bad. So when we looked at whether or not we have this dummy variable, so now a 1 unit change is going from the 0 to the 1 group. So a mother who smokes while during the pregnancy relative to one who doesn't, we would expect the predicted change in birth weight would be whatever beta 1 is. If you run this regression, you'll find a pretty large negative value. But the smoking while pregnant actually caused that much detrimental harm to the baby, right? Sure, it is bad, right? But is it actually that large of an effect? Well, maybe not, right? Because guess what's also correlated with smoking while pregnant? Probably not caring about a lot of other things that you're doing while pregnant that are going to be bad, right? You're not eating as healthy of foods. You know, it's actually, if we look at kind of smoking, it's correlated with low income. So maybe you don't even have just access to high quality foods. Maybe you don't have access to healthcare, right? All these other things that are likely to have negative effects as well. If you don't control for them, they get kind of baked in to this effect that you find. Now, as you start to control for those factors, you're pulling out the impacts of those things now because you can hold them constant, right? Or we're eliminating what we say bias in our estimator. Okay? So I did this one week 1 too, but you know, autism, organic food sales, looks like there's a pretty strong positive correlation. We got to control for other things. One of the, you know, autism is not being caused by organic food sales. This was also week 1, right? I used to think correlation implied causation. I took a stats course, now I don't. Sounds like the class helped. Well, maybe, right? Maybe you're actually in the class because you're already smart enough to understand this, right? And so this is what we eventually want to do. We want to move from correlation to causation. The first step is just including these additional control variables. So I've got a bunch of nastiness here that you don't have to worry about, right? So this is like the actual mathematical proof that we're not going to work through. But what we end up with, the end result here, is that whenever you're coming up with this slope coefficient estimate, it will include, right? If we were to take like 1,000 different samples, we said if we took those 1,000 different samples coefficients, they would, the mean of them would be exactly equal to whatever that population slope value would be. But if we leave out important omitted variables, things that are correlated with both X and Y, we're also going to get this additional bias component. So what is that bias component, right? So if I know that this is the actual prediction function or the linear regression I should be using, where I've got both of these variables that influence Y. If I then run a regression where I leave out that second variable, I will get from my slope coefficient estimate whatever that true slope value should be, plus this bias. So this bias might kind of look familiar, but just to explain this first part, this would be the impact that that variable you left out would have had if you included it into your regression. This second thing, well, this is the variance, right, in your X1 variable. Here's the covariance between the variable you included and now the variable that you've left out, right? So it's like this variable you left out, how is it correlated with the variable you left in? And how is it essentially correlated with your Y variable? That will be kind of the sign and size of your bias here. Okay? So I don't think we'll have time today for me to prove this to you in Stata. I'll probably start out on Thursday with it. But you know, we could actually grab this. So I just told you that that bias is equal to whatever impact that variable would have had on Y if you put it into your regression, times the covariance between those, the variable you included and the variable you left out, and then divided by the variance of the variable you included. So if you remember from last week, we went through this thing where we said, if I were actually to run this regression, another way of writing this slope coefficient estimate was you could have looked at the covariance between X and Y and divided it by the variance of X. So what this is really representing is if I were to run a regression where I was trying to predict that omitted variable using the variable I included, it would be whatever that correlation was between those two. Now, in practice, we're not gonna have to like run this, but that's just kind of where that comes from. We don't have to have that memorized, but we do need to know this will be what gives us our bias, okay? Any questions on this before we keep moving? So I've got like a ton of summary slide here in a second, but maybe I left out a variable. I'll use an example here that we can maybe look through. So let's say I was trying to predict college GPA based off of whether or not you were identified or considered a student athlete at the college, just a 1-0 variable, right? If I'm a student athlete, what do you think is probably true about the admission standards relative to a not student athlete? They're lower, right? So if I don't control for anything else, it's going to look like there's a pretty strong negative effect, right, of being a student athlete. So if I think about, well, what did I leave out there? I left out kind of what was the underlying ability of the student, right? So instead of, what's a good measure I have of that? Maybe I use high school GPA. So maybe I'm trying to predict college GPAs. I run this very naive regression where I just used if they're a student athlete or not, but I left out this second X variable, which was high school GPA. I left this out of my regression. So the slope estimate that I see on athlete will have this bias, which is, well, what would have been the impact if I had included high school GPA and a college GPA? What do you think the correlation is between those two things? Or what do you think effect high school GPAs would have had on your predicted college GPA? Maybe positive or negative. Positive, right? Typically, those people with higher high school GPAs tend to have higher college GPAs. So positive. Well, what's true about my variance? It should always be positive or negative. Variances are always positive. You guys are worrying here, right? We're squaring up the deviations. Anytime you square something, even negatives become positive, right? What would the correlation be, or what would the covariance be? I should be a little more accurate, between athlete and high school GPA. Well, we just said we think that it's likely that they have lower admission standards. So on average, these two things would be kind of moving in opposite directions. So my bias is actually going to be negative. So when I'm getting that slope coefficient estimate, it'll have the true effect of being a student athlete, but it'll also have this bias, which we just said is going to be negative. So the estimate I see is going to be even larger than what it actually should be. So maybe I see, that being a student athlete will lower predicted college GPA by -0.5. Well, the actual effect might be something more like -0.2, right? Because we're kind of baking in, we haven't controlled for this other factor, which is that on average, that student athlete group is going to have lower high school GPAs. So we can put a sign to our bias, is essentially what I'm getting at here. And we'll start with this next class, but I have there you go. Kind of, we can have all these different combinations. There we go, right? Maybe that beta 2 could be positive or negative, and then the covariance between that variable you left out and the variable you included could be positive, negative. And we can actually put like a sign to the bias that we would see by leaving out that what we call an important omitted variable. Right? So we'll pick back up on this. Just want to kind of get it introduced today. Because, well, yeah, I do this. Let me think if there's anything else I want to say. Of course, I already jumped the gun. Well, I'll show this to you since we already used this example. But I'll start out kind of working through different examples of signing the bias, putting a sign to what that bias actually is. So if I looked at like this GPA, and I think here instead of using high school GPA, I use their SAT score. Same idea, I'm trying to get some underlying measure of their ability. If I just run the naive regression where I left out that important omitted variable, it looks like being a student athlete predicts lower GPAs, quite a bit lower. 0.3 is pretty significant in a GPA, in terms of GPA. If I include that SAT, now holding constant the SAT score of the individual, so the thought experiment is two people in college with the exact same SAT score, but one of them is a student athlete, the predicted change in their GPA in college would be only about 0.05. So that's quite a sizable change, right? And it's not even quite significant now. So I actually can't even say 0.26 is my p-value. I can't even say that being a student athlete has any negative impact on your GPA, holding constant the SAT score. Now, there might be other things I want to kind of factor in. In fact, I had this data set for a while. I'll try to use it later on. It's kind of interesting if you start to throw in more controls. Being a student athlete actually has a pretty strong positive effect, because if you're a student athlete, you have more resources available to you. You have to have like almost forced time management. But we think of it in this way of all the things it's correlated with. But once we include those in our regression, we're holding all those factors constant. So we'll pick up on this kind of finish this correlation causation last class. I'll show you some stuff in Stata that we can do related to it. We'll use this multiple linear regression in class. So I've got kind of that wage data. We'll run through kind of some bias examples with it. So what I want to do though, the last 10 minutes here is incentivize attendance, because I can see people that don't show up, I get questions about things that I know I for sure said in class. So 12, so try everything set correctly here. Yes. So you should see this now pop up on Canvas all the way down here under module 4, right? So these are, once again, extra credits. So I have to kind of rearrange the grade book. Once we get that first problem set graded, I'll kind of rearrange it so that your grade on Canvas is being calculated according to the syllabus, weighting the quiz and problem set categories accordingly. Also, these in-class participations are just for extra credit. Okay? So showing up here should be pretty easy. We'll walk through these. If you're paying any ounce of attention, everyone here should get full points, right? And it closes out as soon as we're done. Right? So also gives us some additional examples. This will be even easier than the stuff we were just talking about. So let's go back to some dummy variable stuff that we talked about last week. So here I've got a search vehicle dependent variable, which is the one if the vehicle was searched at a traffic stop, 0 if not. I then have kind of this black indicator variable, which was the individual considered black, 0 if they weren't. Right? So how would I interpret my intercept or my constant here? So how do we interpret an intercept? It's when the x variable is equal to 0, it's the predicted value of y. So here, what would the x variable be equal to 0 mean? If the individual that we're looking at, the traffic stop, was considered not black, the predicted probability their vehicle is searched is 0.019. And I think here I've got it rounded to the second decimal, so 0.020. So if the driver is not black, probability that x value is equal to 0, the probability their vehicle is searched is 0.02. So that should be pretty easy, right? Hopefully everyone's getting this one correct. Right? Now, what's a little bit more interesting, I shouldn't say more interesting, but kind of bad. What if I interpret my slope coefficient? So we didn't do a lot of these where I've got an independent and a dependent variable that are 1 zeros, 2 dummy variables, right? So how would I interpret my slope coefficient on that black variable? So what's a 1 unit increase? When if I have a dummy variable, it's looking at the 1 group relative to the 0 group, right? Going from the 0 to the 1 group. So for an individual who is considered black, this traffic stop, relative to someone who's not, what is the change in their predicted probability that the vehicle is searched, right? So this coefficient, when we have a 1, 0 dummy variable, that's our dependent variable, its changes in the units are probability. Right? We walked through some of this last class. So here, it's about 0.037 higher, or there's about a 3.7% chance more likely, right, that the vehicle is searched if the individual is black, right? So Tyreek Hill, right? So I mean, we have this, right? We see things actually play out. Now, if I control for a lot of other factors, I'll be completely honest, I have this data set. This effect does get lower. It's not quite as large, but I'll tell you, because I've played around with this and I've got it up there on Canvas. We'll start using it more next class, that traffic stop data. I think I actually opened it up at the beginning of class just to show you how to open up a file. It does get smaller, but it's always statistically significant, right? It's always that we can say that there is an effect on this vehicle search of whether or not the individual is black. So not great for society. So Our second question should be a relatively easy one. What levels can I reject the null hypothesis at? So I'm setting up some easy softball ones here because I just want to make sure we're all able to get these easy stuff because we're going to keep on making it harder and harder as we progress. So here I had college GPA and high school size. So what levels could I reject the null hypothesis that the high school size has no predictive power or no correlation with college GPAs? Yeah.
10% of one.
Yep. I've got a p-value of 0.06. Is that less than 0.1? Yes, so I can reject the 10% level. What am I rejecting? I'm rejecting that there's no relationship. Can I reject at the 5% level? Well, alpha is 0.05, not quite. And if I can't reject at the 5, I definitely can't reject at the 1. Once again, these significant levels, they work opposite of confidence. So I'm really saying I can reject with 90% confidence, but not with 95 and not with 99. Okay. Now, I also wanted to use this one to kind of make a point. How would I interpret the slope coefficient here? So we're going to start looking at variables that have weird scales. So the units sometimes will be a little bit different. So this looks like a really small effect. But if we look here, a high school size is going to be measured in hundreds. So if this variable was a 2, that would represent actually 200. So a 1 unit change going from a high school size of 2 to 3 is actually what kind of an increase? So not just 1, right? If the high school size, I say, like it's in hundreds. So 2 would represent 200 students. 3 would represent 300 students. So a 1 unit change in this high school size variable going up by 1 is actually an increase of 100 students. So being in a high school that is 100 students larger would actually predict that your college GPAs are a little bit lower. Right? Now, once again, having control for a lot of other factors, we could probably come up with a story maybe though about why getting lost, having much one-on-one attention at a higher, but we can, be cautious with these results because we know there's a lot of other factors that matter that we're not controlling for. And that's what we essentially started to do today and we'll continue to do next class. Okay. And then I think the last question I have here, hopefully is a no-brainer for everybody, which is click, kind of get the base points, click yes here. Right? So make sure you get that done before you leave class today. I'll extend the due date on that assignment, first problem set to the end of the day tomorrow, right? I'll be in my office. If you want to stop by during office hours tomorrow. I'll also put up the second quiz and the second problem set. Other than that, I'll see you guys on Thursday.